Good evening, beta. So let us try to firstly revise the mechanical properties of solids, beta. Directly, I'm going for the applications of this one. Surface tension. First formula in surface tension, beta. How do you define the surface tension? Surface tension is represented by your letter T. Surface tension, capital T is equals to force acting per your unit length. Okay, or else F is equals to how much for me? T into your L. Clear, beta? Units will be, can anyone tell me the units of this one, beta? Force is measured in Newton, length is measured in meter, Newton per meter. Okay, see this one. If I'm talking about the surface tension or surface force, surface tension force on a wire of length, say for example L, placed on water, F will be equal to your 2T into your L, because when this wire is being kept on water like this, on this side there will be a surface tension T, and from other side there is a surface tension T. So this one is being exerting the surface tension force in the upward direction. So that is the reason we are getting here 2 beta. So F is equals to your 2T into your L. Clear? The same way, if I am talking the surface tension force on circular disc, surface tension force on circular disc, beta, on your circular disc of some radius, say for example small r. Okay, like say this is your disc of radius of your small r, and it is totally immersed in the water. Sorry, not immersed, kept on the surface of water. A force required to pull it in the upward direction. So F will be equal to your T into its length. Length will be equal to perimeter. So that perimeter will be equal to how much perimeter? 2 pi into your r. So that will be the length. So force required on a circular disc to lift in the upward direction is F is equals to your surface tension force is equals to your T into your 2 pi into your r. Clear, beta? Now see, if I'm talking about the ring, beta, ring has 2 surfaces. So just multiply this one with your 2. We'll get the answer. Surface tension force on a ring of radius capital R, something like this. Okay, so for this one, F will be equal to your 2 into its length is 2 pi into capital R into surface tension T. So F will be equal to your 4 pi R into your capital T. Okay. So these are the basic formulas you need to remember in the surface tension, beta. Surface tension is T is equals to force per your unit length, or F is equals to T into your L. Unit is Newton per meter. Clear? Now, next one is surface energy. Surface energy. Surface energy. That means the extra energy that the surface of the film has is called as a surface energy, beta. Generally, the molecules on the surface has a greater potential energy than the molecules which are being inside. Okay, like say for example, if I take a liquid like this, the molecule which is totally inside, it is in equilibrium. Like say on this one, if I'm taking, all the forces are in the equilibrium, so it is totally in equilibrium. Whereas if I take the liquid which is on the surface right now here, there is one force here right now, one force here right now, this is one force here, this is one force here, this is one force here right now. So molecule in the surface has a greater potential energy than the molecule which is inside the liquid beta. Okay, so the one which is having on the surface has more potential energy. Okay, than the compared to the liquid which is been totally inside the liquid part. So the extra energy that the surface has is called as the surface energy beta. Or the another form to define this surface energy is nothing but work done in increasing the area of your surface film. So work done, I can calculate the formula here right now. Can write here a molecule in the surface or on the surface, I can say, has greater potential energy than a molecule which is inside the liquid, okay. So the extra energy that the surface film has is called as of your surface energy beta. The extra energy that a surface film has is called surface energy. Okay, so that is a basic thing you need to remember for the theoretical question beta. That's it. The next one is about your work done. Work done in increasing the area of surface film. Okay, very important formula. 90% questions are being based upon this only in your NEET examination. Work done will be defined as the product of surface tension into your increase in area of your cross section. Okay, so for a breaking of a liquid drop, okay, into n number of droplets, for breaking of a liquid drop into n drops. See, I'm drawing the diagram. This is one larger drop of radius, say for example capital R. It is breaking down into your n droplets like this. The radius of this one is smaller, isn't it? So work done will be equal to, area is more for where beta? This is having more area beta. So this is the final area. This is your initial area. So here final area is greater than of your initial area. So work done will be equal to your T into your A2 minus of your A1. That means final energy minus initial area. So it is T into your n number of droplets n into 4 pi into small r square minus initial area of the droplet is 4 pi into capital R square. So work done will be equal to your T into your 4 pi will be common into n into small r minus of your capital R square. So this is the work done in breaking a larger, bigger droplet into your smaller droplets. What is the relation between small r and capital R beta? Anyone? Relation between capital R and small r. Very famous equation. Like say we are having a larger droplet of this one of radius capital R, and it is breaking into your n number of droplets. So initial volume must be equal to final volume. So volume will be equal to 4 by 3 pi into your capital R cube, and it is breaking into n droplet on them. So it is n into 4 by 3 pi into your small r cube. 4 by 3 will get cancelled right now here. So I can write here capital R cube will be equal to your n times of your small r cube. So capital R will be equal to n to the power of 1 by 3 into your small r. So capital R is equals to your n to the power of your 1 by 3 n to the power of 1 by 3 into small r. Like say if capital R and small r been given, I can convert that one and write them here right now beta. So small r will be equal to your capital R divided by n to the power of your small. Clear? Now generally soap bubbles has two surfaces beta. Soap bubble has two surfaces. Okay, so work done will be equal to your T into your 2 into. Okay, so whatever the surface area we are taking, so 2 times we need to multiply beta into your delta A. That will give me the answer. Okay, like say example, if I'm giving you work done in blowing a soap bubble from 0 to radius capital R. That means initial area will be equal to 0 and final area will be equal to 4 pi into your R square. So work done will be equal to surface tension into your A final minus A initial. Initial area is 0, so work done will be equal to T into 4 pi into your R square. Clear, beta? Okay, into. For the soap bubble, two surfaces. So work done for your soap bubble will be equal to your, how much for me? 8 pi R square into T. So this will be the work done in forming a bubble from 0 to the radius of your capital R. Clear, beta? So next heading, pressure difference. Pressure difference. Okay, first one. In a liquid drop, if I'm taking, I hope you remember this formula, Nandini. For a liquid drop, excess pressure is P inside minus P outside will be equal to your 2T divided by your capital R. The same way, in a soap bubble, if I'm taking, in a soap bubble, excess pressure is P inside minus P outside will be equal to 4T divided by capital R. Okay, so I can write here, in general, for one free surface, excess pressure P initial minus P naught will be equal to your T into your 1 by your R1 minus, plus 1 by your R2. So general formula for the excess pressure is Pi minus of P naught will be equal to. Done, beta? If R1 and R2 are same, 1 by R plus 1 by R. So it is 2T by your R. That will give me the answer for that one. For the soap bubbles, you just multiply it with your into 2. So soap bubble always has of your two surfaces. Clear, beta? Clear, beta? Sure. Next one, angle of contact. Angle of your contact. See, first point. See, it is a property of material of the contact, beta. It depends upon that whether it is wetting or not wetting will depend upon your angle of your contact. So I can say that angle of contact is the property of material in contact. Material in contact. Like if it is greater than 90, lesser than 90, then whether it will wet or not, that is the basic thing on which we will be deciding when it will be wet or when it will be not wetting. Another very important point, beta, it decreases with the temperature, angle of contact. It decreases with increase in temperature. Clear? And also decreases with addition of impurity. It decreases with the addition of impurities. With the addition of like soap and detergents. Okay. And whereas it increases with addition of the sugar and salt. Okay. It increases, very important point, but it increases with the addition of your sugar and your salt, like electrolytes, what we call. Okay. Next one, angle of contact of water with your glass is 8 degree, is your 80 degree. And for mercury in glass is more than 100, so it is 140. It is an NCRT point beta, you need to remember. Angle of contact is a property of material. It decreases with increase in temperature, decreases with addition of the impurities like soap and detergents or whatever impurity you take. Whereas it increases with the addition of your sugar and salt like electrolytes. Angle of contact of water is 8 degree and that of mercury with respect to glass is your 140 degrees. Clear? And next one is capillary rise. Capillary rise. Okay, now see, this is your capillary tube, a small bore. When it is immersed in the water, the liquid will be rising like this. I'm not interested in the derivations of this one better because it is of no use also. And if I'm taking this one right now, the radius of this one is right now for me equal to your r. And this is the radius of curvature of this circular path. Okay, so radius of this one from here to here will be equal to your small r. Okay, so small r is your radius of capillary tube. Okay, and this is the circle. So from here to here, this represents the radius of curvature. Capital R is the radius of curvature of, capital R is your radius of curvature of liquid. Okay. Now what is the formula beta? Very famous formula. H is equals to 2t into your cos theta divided by your RD into your G. So height of the liquid in the capillary tube is being calculated. If the water is being raised up to a certain height, so this height can be calculated with the formula H is equals to 2t cos theta divided by your RD into G. D is the density of liquid, R is the radius of capillary tube, capital T is the surface tension, theta is the angle of your contact, and H is the height of the liquid raised in your capillary tube. Clear, beta? In terms of radius of curvature, if I am writing, beta, in terms of radius of curvature, that is capital R is equals to small r divided by cos theta. Very, very important relation between capital R and as well as of a small r. So therefore I can write height of the liquid in capillary tube will be, now see, cos theta divided by R can be written as beta 1 by R. So H will become how much for me? 2t divided by your capital R into rho into your G. So this is the formula we need to remember here. Okay. Now in case of a square plate, beta, in case of square tube, in case of your square tube of side A, height will be equal to H is equals to 4t into your cos theta divided by area into density of liquid into G. Okay. 4t cos theta divided by A rho into your G part relation. Very, very important. So capillary tube in a liquid. So whenever a liquid is being, or whenever a capillary tube is being inserted into the liquid, the rise of the liquid in a capillary tube is calculated with the formula H is equals to 2t cos theta divided by R into D into your G. Where your D is your density of liquid, R is radius of capillary tube, capital T is surface tension, theta is your angle of contact. A relation between the capillary and small r, where capillary is radius of curvature, is capillary is equals to small r divided by cos theta, or H is equals to 2t divided by R into rho G, because the reverse of this one. This R cos theta by small r can be written as of your 1 by 2, isn't it? So 1 by R will be equal to your, so this will become for me cos theta divided by small r. So that is the reason I'm writing this one right now. Clear? Sure. So in case of square plate, it is instead of the 2t, we'll be writing it as 4t. Instead of your radius, we'll be writing the side of your tube. That is nothing but of your E. Okay, sure. Next one. Very important one, better. Capillary tube. Capillary tube of insufficient length. Capillary tube of your insufficient length. Okay. It's here. If small h is the free rise of liquid, the free rise of the liquid, free rise of your liquid, and and say L is length of tube, length of your tube. Okay, like so this is your capillary tube. In this one, there is a free rise of the liquid in this one. Total length of this tube is, say, for example, L, and this one is your height of your H. Clear, beta? If H is the free rise of the liquid and L is the length of your tube in this one. Okay. So if L is, now I am writing right now, if L is lesser than of your H, then H into your capital R is equals to L into your R dash. R dash is the radius of the meniscus of the liquid beta at the top of your tube. R dash is radius of curvature at top of tube. Because it will try to overflow, no? Because if length is lesser than height, then it will try to rise up to a certain height, then it will try to fall. Before falling, it will form a circle. Like say, if the height of the liquid is like this, then before falling, the level of your liquid will go like this. It will form like this, isn't it? So it will try to fall on that one given condition. Okay, beta. So the liquid will not spilled out. Clear? So I'll write here one condition. The liquid will not spill out. It will not fall down. Spill out as L is lesser than H. So R dash will be greater than capital R. Isn't it? So obviously it is not going to fall down. Clear, beta? Next one. Apparent angle of contact. Apparent angle of contact. Apparent means false. Change, or you can say not false. Okay. If theta and theta dash are true and apparent angles. Direct application beta. Apparent angle of your contact. Then cos theta dash will be equal to your L by H into your cos theta. Very important relation. Okay. And one more. Force required to pull the plates apart. Like see, when we go for the blood test, they'll try to take the blood and try to keep between the two plates. So whenever a liquid is being kept between the two glass plates and try to pull it out, they will require more amount of energy to pull them. So force required to pull the plates, and A is, so like say it is having some liquid or something like that. Some plates apart, having some liquid between them. So it will be equal to your F is equals to your excess pressure P naught minus P initial into your A. So that will come out for me 2T divided by your A divided by your small d. P naught minus Pi means I got here right now. See. P naught minus of your this one. 1 by R1 minus 1 by your this one. If radius of curvature on both the sides are same, so that will become for me how much beta? T into your 2 by your R. So thickness. That is the reason I'm writing here right now. 2T by your A. Small d is the separation between the plates beta. Like see, if the plates are something like this, the liquid will form like this. And this one. This is your T. So small d is nothing but what beta? Separation between plates. Okay. And area A is your area of cross section. A is the area of your each plate I can take. Clear, beta? So these are the basic things you need to remember for this one. And apart from this one, we are having some shortcuts to do the problems better. First one and very famous is when two soap bubbles of radius R1 and R2 are in contact, then what is the radius of curvature of the contact point? Like say for example, I'll write here when two soap bubbles of radii small that is R1 and R2. If they are in contact, the radius of curvature of contact point like this. If there is one drop like this and another drop like this. Okay, and this one is having a radius of R1 and this one is having a radius of R2 and this one is your common radius. Okay, and this is having a common radius. So this will be equal to your common radius will be equal to your R2 minus of R1 divided by your R1 into your R2. Direct application better. If you go for the proof and see it will be waste of time. We need to remember that whenever two soap bubbles of radius R1 and R2 are in contact, the radius of curvature of the contact point will be equal to your R is equals to your R2 minus of your R1 divided by your R1 into your R2. Clear, beta? Is that clear? Sure, next one. The difference of the height in the liquid, beta. The difference of height in a liquid in U-tube, in your U-tube. Let's say U-tube is something like this. Okay, and there is a liquid in this one. Okay, and if I'm taking from this one beta, the reference, this is the difference of your height. That is delta H. This one is having radius R1 and this one is having radius of R2. Clear, beta? This is the formula. Delta H is equals to 2T by your rho G into 1 by R1 minus 1 by R2. Very, very important bit. And one more important point, mass of rise of liquid in capillary tube. In your capillary tube is mass is directly proportional to R. Once already asked in the NEET examination beta based on this one. Mass is directly proportional to your R. Clear, beta? Is that clear? Sure. Let me give you one example. Do this question with two rectangular plates are placed at a small gap. At a small gap T. Okay. My question is find rise of liquid. Find the rise of your liquid between them. Okay. So angle of contact theta is equals to like 0 degrees. Okay, beta. Two rectangular plates. See something like this. Okay, when liquid is being taken right now, there is one rectangular plate like this. Okay, and there is another rectangular plate like this. Okay. When it is inserted in the water, the liquid will rise like this. Okay, two capillary tubes right now. So in this one, there is a rise of your liquid in this one. So this is the length of this one, beta. And this is the thickness. This is your T. Two rectangular plates are being placed at small gap. The gap between them is how much for mu T. Length of that one is, say, for example, L. What is asking is rise the level of the liquid to which the liquid will be rising in this one. So what is the height to which it will be rising? See here, whenever the liquid is rising, beta, the weight of the body acts in the downward direction mg. So surface tension force is F is equals to your m into your g force. Here the force is because of surface tension, so it is a T into your 2L, two surfaces covered, that is equals to your m into g. Mass is equals to volume into density into g. Here volume will be equal to how much, beta? Volume is equals to length into gap between them into height to which it is been raised into your g. So it will be T into your 2 times of your L. So anything is getting cancelled in this one. This L will get cancelled. So what is asking rise? That means H. So this one is 2T is equals to your H into thickness T into your G. Thickness is nothing but gap, beta. So H will be equal to how much for me? 2T divided by your this one is volume into density is also there, rho. So into your rho. So this will be equal to your 2T is equals to that much. H is equals to 2T divided by your, this will become for me rho T into your G. So this is the height to which it is been raised. Done? See it once again, beta. Surface tension formula T is equals to F by L or F is equals to T into your L. So force will be equal to your 2T into your L part deflation. The surface tension on a curved or circular disc will be equal to, so total circumference is 2 pi into R. And for the soap bubbles, you take it as if you have two beta, two surfaces. And work done formula, these are the basic formulas, beta. Small topic only, you just go through it. And basic important formula is H is equals to your 2T, I is right of the liquid. H is equals to 2T cos theta divided by your R into your dg. And relation between capital and small r is equals to small r divided by your cos theta. Remaining this all, you can just go through it better once. And this is again important formula. The difference of the height of the liquid in the U tube is delta H is equals to 2T divided by rho G into 1 by R1 minus 1 by R2. And mass of the rise of the liquid in a capillary tube is directly proportional to your radius. Okay. Small topic, better. Depth is not required. That is the reason I'm directly going for the application for this one. Okay. So try to prepare for tomorrow's examination better. Basically, direct formula based problems are based upon this one. You can just go through it. Okay, Nandini? चलो स्टूडेंट्स కూడా ఎవరు లేరు, so I'm stopping the class beta. Okay, take care, bye beta.